So our question asks, a particle is moving along the curve y equals root x. As the particle passes through the point 4,2, its x-coordinate increases at a rate of 3 centimeters per second. How fast is the distance from the particle to the origin changing at this instant? So first of all, I'm just going to take down some things that is given. So I'm going to take down the displacement curve for the particle, which is just going to be y is equal to root x. I'm going to take the derivative of this just so I know that its rate of change, like the y prime for the particle. So y prime is just going to be equal to x prime times 1/2 x negative 1/2. So I'm writing it in terms, I'm differentiating implicitly just because I'm writing x prime I'm writing it in terms of z prime. The final answer is going to be in that terms. I'll show you that in a second. But anyway, that's just going to simplify to y prime is equal to 1/2 root x times x prime. Okay, so it also gives me a point modeled on the curve 4,2 where the rate of change of the particle is 3 centimeters per second. So that's just going to be the x prime. You're going to see this modeled in a second where I'm going to give you the equations. So it's asking for how fast the distance from the particle to the origin is changing at this instant. So it's almost going to be a triangular question. So it's asking, so we know this is going to be the x and y. It's going to be the point where the particle is, and it's going to ask for the rate of change of this displacement to the origin. So this is going to be modeled by the Pythagorean theorem. So z is equal to root x squared plus y squared, where z is just the displacement between the 2 points. This can also be modeled as z is equal to x squared plus y squared to the 1/2. I'm just going to take the derivative of this to find the rate of change of this displacement z from the particle point to the origin. So z prime is going to be equal to the derivative of the inner, which is going to be 2x times x prime plus 2y times y prime times 1/2, just the outside derivative, which is going to be 1/2 x squared plus y squared to the negative 1/2. Okay, so I'm going to start plugging in some points that I know. So I know that our x point, it gives us an x point on this curve, the 4,2, as well as a rate of change of the particle, or the x-coordinate, which is x prime is equal to 3 centimeters per second. And also I know from up here that y prime is just going to be 1/2 root x times x prime. So again, I'm just going to write those terms in. So 2, our x value, times 4 times x prime, which is 3, plus 2, our y value is 2, times y prime, which is 1, or x prime, all over 2 root x. So x prime is just going to be 3, and root x is going to be 4. Then I'm going to do 1 times 1/2. Alright, and then our x point, which is 4, plus our y point, which is 2, to the negative 1/2. Okay, now I can write this term, simplify this out a bit. So z prime is just going to be equal to 8 times 3 plus, so this is a 4 right here, and this is also going to become a 4, so 2 times root, so 2 times 2, which is going to be 4. So these two terms can cancel out. It's just going to be times plus 3, sorry, here, and then times 1 all over 2 root 4 squared plus 2 squared. And then this is going to simplify out to give me prime is equal to 27. This term is going to be 27. It's going to be on the numerator. All over 2. This is going to be root 20, this term here. Root 20. And this is going to give us approximately, if I do the math here, just 1 second. I apologize, I was plugging that all into my calculator, but this is going to give us approximately 3.019 centimeters per second. So this is the rate of change for the particle's position to the origin, which is just going to be 0, 0. So this rate of change, the particle's moving away from the point of origin at this point, for 2 at 3.019 centimeters per second. Thank you.